Ladies and gentlemen, welcome back to Theoretical Chemistry. Today we honor Valentine's Day. Today we're looking at chemical reactions, in particular the different types of chemical reactions, and it will center on our lovely relationships. So today, as we look at our chemical reactions, we've got count them, five different types of relationships, five different types of reactions that we need to know. Our first type, single displacement reactions. Single displacement. Remember that, type 1, single displacement. Sometimes could be replaced with single replacement. We're going to use single displacement. Well, second type, double displacement. Double displacement, a little bit different than single displacement, obviously, a little more going on there. Our next type is synthesis, followed by decomposition, followed by combustion. There are 5 types of chemical reactions. All of the reactions that we see in the lab can be broken into these 5 general categories. Again, that's single displacement, sometimes abbreviated SD, double displacement, sometimes just abbreviated DD, synthesis, abbreviated S, decomposition, abbreviated D, and C, combustion, is our 5th and final type. Now, I really like thinking about these like relationships because there are a couple different types of relationships that you will see, and we can apply those to our chemical reactions. So our first type here is our single displacement reaction. In a single displacement reaction, one element displaces another in a compound. Ladies and gentlemen, this is an affair. Right? So here's your happily married compound, your happily married couple, and along comes a red hot lava. In this case, the chlorine. The chlorine, so that would be like Angelina Jolie, right? And then here's Brangelina, right? Got Brad Pitt, Jennifer Aniston, right? So we got a happily married couple, red hot lava, and the red hot lava comes along and gives that one element the boot, das Boot, making a new compound and booting out that extra element. So it's an affair. Another way to remember it, single displacement, we got one element reacting with one compound to make one new element and one new compound. Single displacement, doing one swapping out further. Now, would the chlorine and the bromine ever want to get together? What do you think? What type of element is chlorine? Well, group 7, that's a halogen. Bromine is also a halogen. On the charge of a halogen, we've got a -1 charge. The chlorine and the bromine are never going to want to get together because they have like charges, and like charges repel apart from each other. So they'll never get together. Got to match up those opposite charges. You'll notice we got the Cl2 here and the Br2. Remember, those elements are diatomics. Hofbrinkel, always partner up. In generic form, we've got A plus Bx making Ax and B. In this case, the metal replaces the metal. Nonmetals replace nonmetals. You never see nonmetals together. You never see metals and metals together. Don't do it. They just don't, because they have like charges. They repel away from each other. Cool. Our next type of reaction is our double displacement. This is kind of like I think of it as a wife swap. That TV show where they flip flop the wives and then they swap back, or husband swap, spouse swap. They're doing a double switcheroo, double do-si-do. Excuse me. So in a double displacement reaction, we have the positive and the negative portions of two compounds flip-flop spaces. So if this was our reaction, zinc bromide reacting with silver nitrate to make zinc nitrate and silver bromide, what we actually had occur was a double switcheroo. The metals flip-flop spots to get it so that we have two new compounds. So now keep in mind, single displacement, one element, one compound. Double displacement, two compounds flip-flopping to make two new compounds. Keep it in mind. Watch, see how they're different. Single displacement, element, compound. Double displacement, compound, making two new compounds. Cool. Generically, we see this as two compounds. Again, two compounds, flip-flopping parts. Flip-flopping partners. Easiest way to get these to be created is to swap the metals. Flip-flop the metals. Right. Next type of reaction is a synthesis reaction. Well, if we're talking about relationships, synthesis, if you synthesize something, you put it all together. In a synthesis reaction, you take two or more substances and you combine them together to make one new substance. So really, a synthesis reaction is like getting married. You got your different parts, different reactants, you smush them all together to make one final product. That's a synthesis, making one new family. Right? So here is our final product. If you only have one product, it has to be a synthesis reaction. Everybody's combined together to become stable. All right. So generically, we take A and X, stick them together, and make AX. Put all the pieces together. Cool. Next, we have the opposite of synthesis. We have decomposition. If synthesis is marriage, decomposition is divorce. I know, I hate to talk about that during Valentine's Day, but it's tight. It happens. Decomposition, you break apart. Sentences break apart or decompose. I think of like, CSI, you got the body that's decomposing, or your compost heap. You got all those fruits and vegetable peels are all breaking down into dirt. Decomposing, you break down into simpler, smaller substances. Now the key here is you got to supply some energy. So here we've got H2O2, which is actually hydrogen peroxide. You've got a bottle that's probably at home in your refrigerator, and you'll notice it's in that dark container to keep it from breaking down into water and oxygen. So a little energy gets put in, light or heat, and the H2O2 kick off an oxygen, leaving water behind. Okay? It's the opposite of synthesis. It's divorce, decomposition, breaking apart. So here AX splits back apart into A plus X. Okay? Last, certainly not least, we have what my students have in the past have generally really enjoyed is our combustion reaction. In a combustion reaction, we take a compound, typically a hydrocarbons, carbon and hydrogen, and it's going to burn the presence of oxygen to make two products, carbon dioxide and water. So you always see the same kind of setup for combustion. Hydrocarbon, oxygen, make CO2, water. Always. Kind of a lame reaction, really, because hydrocarbon, oxygen, burn, carbon dioxide, water. It actually makes sense. In a fire, you gotta be careful. In a combustion reaction, in a fire is actually eating up or using the substance you want, the oxygen part we take in, and giving off our waste product, the carbon dioxide. So we're actually trying to compete with the flame, with the combustion reaction, and all the while we're trying to get oxygen. It's quite literally being sucked out of the room, being changed into carbon dioxide, which our body can't use. I've thought for a long time, trying to come up with a good analogy for a combustion reaction. I've got two. You can kind of choose your one. So we got synthesis, adding together, marriage, decomposition, one reactant breaking apart, divorce. We got single displacement, one element, one compound, flip-flopping apart. That's our affair. Double displacement, like wife swap, old TV show. For combustion, the only real good example I've been able to come up with is kind of like John and Kate plus 8. We got these very specific situations and under the right pressures and the right amount of energy, all heck breaks loose, right? Had heard another really good one. Student came up with this one actually. It was kind of like Romeo and Juliet. That you got certain families and the right situation, all heck breaks loose, and we get very specific outcomes. You always get carbon dioxide and water in the event of a combustion reaction. Cool. So those are your 5 types. If you want to go back, relook at some examples, they are there. Might not have been a bad idea to just kind of jot down what some of these different types are. Good information for you to have as we move forward. So now what we can do is we can look at a chemical reaction. And we can say, okay, what type of reaction is that? Based upon the reactants and the products, what type does it belong to? Cool. Awesome. Excellent work today, guys. And we are now moving on.